Spin splitting. Whenever we see this term, we remember one rule, that is n plus 1 rule. This helps us to know what kind of peaks we get in NMR spectra. For example, in this given compound, we have 3 hydrogen atoms present. These 2 hydrogens are bonded with this carbon, which is attached to chlorine and this carbon. So these 2 hydrogens behave similarly. So we call this as equivalent hydrogen. We can see that here in this bond, the electrons are shifted towards the chlorine because of its electronegativity. So these protons are de-shielded. In this carbon, we have 1 hydrogen attached, but we have 2 chlorine atoms here. So the electronegativity will be more, and these electrons are more shifted. So this hydrogen is more de-shielded compared with these 2 hydrogen atoms. So it is easy for resonate this hydrogen atoms compared with these 2 hydrogens. So this is what we expect in this spectrum. This is the TMS standard. This is for CH2 proton and this for CH3 proton. Under row resolution, we can see a single peak for this CH2 and a single peak for this CH3. We can see that this is more shifted and this is less shifted. This is because of the de-shielding effect. Under high resolution, we got, in place of that single peak, we got here peaklets. For CH2 we have doublet, and for CH3 we have triplet, 3 peaks, here 2 peaks. The number of peaklets that we can get for a particular proton can be calculated using n plus 1 rule. So here we can see for these 2 protons are equivalent. So the neighbor has single proton. So it is n plus 1. So n is 1 plus 1, it is 2. So for this 2 CH2 protons, we got a doublet. And for this CH proton, we have here 2 different 2 hydrogen atoms. So in place of n we put 2. So 2 plus 1 is equal to 3. So for this CH3 proton, we got a triplet. Let us know more about how we got these peaklets. We place this molecule in a strong magnetic field. So first we are going to study the peak obtained for this hydrogen. This is the applied field H0, and we are going to study the peak obtained for this hydrogen. So there are 2 adjacent hydrogen atoms. The possibility can be these both are in the same direction, align itself in the direction with that of the applied magnetic field. So this is the induced magnetic field. So the nucleus which experienced magnetic strength will be more than the expected value. So in this is the expected value for this proton, particular hydrogen proton. But due to this kind of alignment, we can resonate this even in less energy. So it shifts towards this side. So we get a peak here. So this is the expected peak, but what we observe is this peak. And the other possibility is this is the H0 applied magnetic field. Here one proton can be align itself with the magnetic field which is applied, and the other can be in opposite way. So this effect get cancelled, and the proton which this experience is only due to the applied magnetic field. So the expected value and the result which obtained will be same, and we get here an intense peak. The third possibility is that both these hydrogens are in opposing way, that is their magnetic field is in opposite to that of the applied magnetic field. So here the nucleus which experience the pull will be less, so the peak shifted towards higher energy and we get here a peak. So this is expected, this is the peak which we get. So these are the three different possible ways through which we got three different peaks. So combining all these probability, we got a final peak, that is triplet. So this is for the first condition, this is the expected intensity, and this is the third case. So in this way, whatever peak we get is not from a single probability way, but all these we obtain through probability distribution. Similarly for this two hydrogen proton, this is the applied magnetic field, and this hydrogen can be align itself with the magnetic field. So this proton which experience the magnetic field strength will be more, so it is shifted towards lower energy, so we get a peak here. The other possibility for this condition is, this is the applied magnetic field and this can be opposing the applied magnetic field. So here the nucleus experience a lesser strength, so more energy will be required. So it shifted towards the higher energy. So we got a peak here. So these are the two possibilities for this CH2 proton. So finally we got two peaklets here. So here this we call as triplet, and this doublet. In this triplet, the intensity ratio will be 1:2:1, and for this doublet it is 1:1. So this intensity ratio we got through Pascal's triangle. So this is that one. This is for singlet, this is for doublet, this is for triplet, this is for quadruplet, so and so on.